Welcome back. So up to this point, we have done some analysis, the Fourier analysis for the continuous time domain, and we have expressed, we have come up with a formulation, representation that any signal x of t, it can be expressed as a linear combination of harmonically related complex exponentials. So we did one example here जहाँ पे ये coefficients दिए गए थे a0 a1 a2 a3 a minus 3, but the point here was to get a deeper insight how we get these harmonic related components. And we saw here, we did the analysis, and these are harmonically related. Each of these components is periodic with some fundamental frequency which is related by some factor, and then overall signal, which is the sum of these components, is also periodic. Now in the Fourier series, the general expression that we have, this one, I will again rewrite it here. X of t, oh, there's a different one. Peterson's x of t, it's expressed as k running from minus infinity to plus infinity, this coefficient a of k, then e raised power jk omega naught t. Right. Now we need some method to evaluate this coefficient. You see, when you go for Fourier series representation, first method is you will have a signal and you will try to represent this signal as this summation, and then expand the summation and come up with the coefficients, the values of the coefficients. We'll be doing shortly an example like this, but there should be a general method wherein, given an input signal x of t, you should be able to evaluate mathematically these individual coefficients. There should be some mathematical formulation for that. So we will do a bit of analysis. We'll come up with a general expression that is used to compute these coefficients, and then for the rest of this analysis we'll be using those formulations, right? So what we'll be doing, we'll be starting by multiplying both sides of this equation. So x of t, on both sides I will be multiplying by j and omega naught t, fine. K runs from minus infinity to plus infinity, a k e raised power j k omega naught t, and I am multiplying by e raised power minus j and omega naught t. Right? Then I will be integrating on both sides over the time period t. So right now I am assuming that your time interval had the time period, it starts from 0 and is up to t, but sometimes it may be from minus t by 2 to t by 2. In general, you can say I'm integrating this thing over the time period t, which is 2 pi by omega. Okay, अब ये time period कहाँ से कहाँ तक extend हो रहा है, that's a different thing. So right now I'm assuming that this time period, it starts from the 0, the origin, and extends up to t. But there may be a case where the signal is such that the time extends from minus t by 2 to plus t by 2. But in any case, the integral is over the time period t. So if I take the integral on both sides, x of t e raised power minus j and omega naught t, with respect to t obviously, then on this side again I will have 0 to t summation k is equal to minus infinity to plus infinity, a k e raised power j k omega naught t e raised power minus j and omega naught t with respect to time dt. Fine. And then again you can do some analysis. Left hand side बहरहाल इतना ही रहेगा, but right hand side you can take the summation out. So summation k runs from minus infinity to plus infinity, ak, then we can evaluate the integral 0 to 2 because it's with respect to t. ak आप बाहर निकाल सकते हैं, it is a constant. these two exponentials, I will merge them into a single exponential of this type, and then dt. Right? Now the main thing here is this exponential, so let's take this exponential separately, let's solve it separately, then we can solve. So in the meanwhile I will call it equation 1. Yeah, let's continue जो हमारा previous we had reached it to equation 4, I think. Yes, so let's call it equation 5. So we are interested in this integral 0 to 2t e raised power j k minus n omega naught t d of t, right? Complex exponentially, again we can use that Euler's relation. So 0 to t, we will have a cos component, cos k minus n omega naught t plus j sine k minus n omega naught t with respect to dt. So we'll have two integrals, cos k minus n omega naught t, and the other one for the sine. Now please remember that both these integrals are evaluated over one time period. This is important. This will help us to solve these integrals in a much simpler way. So it's not arbitrary that I'm integrating from 0 to t. T here means something. T means the fundamental period. I am basically integrating these two quantities, the cos and the sine, over one time period. Okay, but then again I have two more quantities involved, k and n. Fine, and the value of k and n will actually determine what will be the value of these integrals. So if I start with the assumption that k is not equivalent to n, fine, okay, so then in that case जो मेरे दो इंटीग्रल्स है, जो क्वांटिटीज़ का इंटीग्रेशन मैं कर रहा हूँ, so in that case both cos k minus n omega naught t and sin k minus n omega naught t, they are sinusoidal component. These quantities, they are periodic because we are talking about continuous time domain. और अगर आप एक कोसाइन सिग्नल को या साइन सिग्नल को इंटीग्रेट करते हैं ओवर वन टाइम पीरियड, it is going to be 0. Fine, I will show graphically. If I have a sinusoidal signal, this is its one period. It has a positive half and a negative half. अगर आप इसको इंटीग्रेट करेंगे over this, integration is basically summation. This is its fundamental period. So this half will cancel with this. Same goes for the cosine signal. It's its one period, so we have this half, and two negative halves. So if you try to sum it up, integrate it over, बशर्ते कि you are integrating over one time period, तो इस केस में that time period is the fundamental period. So the total area under this curve will be equivalent to 0. So this means that if k is not equivalent to n, तो जो आपका इंटीग्रल है, this is also equivalent to 0, this is also equivalent to 0. So your integral for k is not equivalent to n, this, if you're integrating e raised power j k minus n omega naught t dt, this will be equivalent to 0, right? Because you're integrating over one period. However, for k is equivalent to n, अब अगर ये बात है कि k is equivalent to n, तो जो आपका इंटीग्रल है, it will be simply e raised power 0 dt, fine, which is 0 to t dt, which obviously is t, right? So we have basically two values for this integral. it will either have a value of t for k is equivalent to n, or it will be 0 for k is not equivalent to n. Okay. So consequently ये जो मेरा equation है, where did it go? Okay, this one, equation 5 actually, it will be reduced to this thing. So 0 to t x of t e raised power minus j n omega naught t dt. That was the left hand side of equation 5. Let me just check. X of t, and on the right side, I will be left, just a second, summation will be there, but it will be something like this. Summation k runs from minus infinity to plus infinity. Let me just first rewrite the entire thing. A of k, and then we had this integral 0 to t e raised power j omega naught t dt. Now see, this integral has a value of 0 for k not equivalent to n, fine, and it has a value of t for k is equivalent to n. Now obviously we'll be taking this value, so this means आपका summation will be defined only for k is equivalent to n, because other than this it is 0, तो आपका पूरा का पूरा right hand side will be 0, and for k is equivalent to n it will be a k t. तो k is equal to n, summation में a की value है, it doesn't make sense, so it is simply a n t, which means जो आपका ये coefficient है a of n, it is 1 by t 0 to t x of t e raised power minus j n omega naught t d of t. Call it 6. Fine. Again, we were trying to compute a of k, but both k and n, they are integers, so it doesn't matter, they both represent integers. So although mathematically they are different representations, but physically they mean the same thing. Fine. So we have basically two equations now. To sum it up, we have the main Fourier equation जहाँ पे आपका x of t, provided it is periodic. This is an important condition, it has to be periodic. It is k is equal to minus infinity to plus infinity a of k e raised power j k omega naught t. Fine. And then to find the coefficients, जो हमने अभी थोड़ा सा analysis किया यहाँ पे, we will be using a of k is equivalent to 1 by t integral 0 to t x of t e raised power minus j. Please don't get confused that I'm using k instead of n. You have to basically see what k and n represent. They simply represent integers. So आप k use कीजिए, n use कीजिए, doesn't matter. They are general representations of integers. Right? Now, this makes up your Fourier series. X of t is a representation. Then analysis के लिए you need to compute the coefficients, जिसके लिए we have the second formula. And equation A, this one, it is referred to as the synthesis equation. Because you're actually synthesizing your arbitrary signal in terms of exponential signals. And equation B is known as the analysis equation, because you are computing the coefficients that helps you to analyze what are the harmonic components in this particular signal. Yeah, in this signal, which has been represented in Fourier as a Fourier series. Okay. And ये जो coefficients है, they are often called as Fourier series coefficients. ठीक है. अब यहाँ से भी आप देख सकते हैं, if you choose a value for 0, if you want to compute a0, so you can simply say a0 is equivalent to 1 by t. You are integrating over the time period t, x of t e raised power 0 हो गया 1. ठीक है. So you are integrating the signal x of t over the time period t, then dividing by t. So this is simply the average value of the signal x of t over the period, over one period. Okay. Now we'll quickly do an example. Like I said, this is the general representation. So जब भी आप किसी signal को, a periodic signal, if it is represented as a Fourier series, then you are interested in the coefficients, because coefficient will basically give you the information about the signal कि कैसे harmonics है इसमें, how are they related, which indirectly will give you the which help in the frequency analysis that we'll take later. So if I take a simple example here, wherein I have the signal x of t, it's a pure sinusoidal signal, sine omega naught t. Omega naught is the fundamental frequency. Okay? And I'm interested in the coefficients. Now you can argue that I can use this, and obviously if you will use this equation, you will come up with the coefficients. But sometimes it is better to use to express this signal as a Fourier series, and you will very well get the component itself. For example, क्योंकि ये pure sinusoid है, so I can express x of t is equivalent to sine of omega naught t. Then you know that it is actually equivalent to, if you express it in terms of what you call the complex exponential, तो ये relation रहता है. So 1 by 2j e raised power j omega naught t minus 1 by 2j e raised power minus j omega naught t. ठीक है. सो विच ऑब्वियसली मीन्स आपने अपने सिग्नल को एक्सप्रेस किया है कॉम्प्लेक्स एक्सपोनेंशियल्स में. सो इसका जो a1 है, इट इज़ 1 by 2j and a minus 1 is minus 1 by 2j. Okay. So you can say, क्योंकि दो ही कंपोनेंट, दो ही हार्मोनिक्स है, सो इन जनरल यू कैन से कि इसके जो कोफिशिएंट्स है दे आर इक्वल टू 0 एक्सेप्ट फॉर के, या दे आर इक्वल टू 0 फॉर के नॉट इक्वल टू -1 और 1, एंड ए के इज इक्वल टू +-1 by 2j and k is equal to +-1. ठीक है. So if you have a signal which is a simple sinusoid, क्योंकि sinusoid में एक ही component है आपका, तो instead of going for this complex analysis, computing the although अगर आप ऐसे भी compute करेंगे तो यही values आपके आएंगे, but sometimes you should be a bit logical and try to express, if it is a simple signal, try to express it directly as a sum of exponentials, and from there on you can get the coefficients. But in general, if we have a signal, for example, we'll take another example. We will do the detailed Fourier analysis here. So here I have a square wave, and the square wave is defined as this x of t. It is having a value of 1 for magnitude of t less than t1, and it is having a value of 0 between this range. Okay. So like I always say, you should first try to plot the signal. So let's try to plot this signal first. So here is my time axis. This is the central part here. So jo signal, it's a square wave, and he's defining it that it has a value of 1 between magnitude of t, magnitude aa gaya, which means it extends on both sides of the time axis. So it will be something like this. Like this. So this is from t1, so this will be okay, minus t1 to cap plus t1 to ye, and this will be obviously 1. So this is the first part of the expression, that it is having a value of 1 when the magnitude of time x is less than t1, so from minus t1 to plus t1. Uske baad it will be 0 from t1 to magnitude, so it means something like this. So I will have a point here, a minus t1, then a point here like this, fine, and this point is actually minus t by 2, and here on t by 2. Okay, so this takes care of this thing, that it has a value of 0 when the magnitude of time is from t1 to t by 2. तो यहाँ से t1 to t by 2, और negative half से it will be from minus t by 2 to minus t1. Now since it's a periodic signal, which means it will extend, so I will may have to extend my time axis just to give you a better understanding how this signal actually looks. Okay, like this, so it will be like this, then again a square pulse, then again यहाँ से भी like this, and this. Okay, so it is a periodic thing, and as you can see जो एक period है इसका, it extends from here right up to this point, minus t by 2, t by 2. That is a fundamental period of t, then it repeats itself. So इसी तरह ये interval भी t होगा, likewise it will be t. Okay, so this is a typical periodic square wave, and it has a fundamental period t, that is the smallest value is capital T, जिसके बाद ये repeat हो रहा है this signal. Fine, and we have to actually we have to compute the coefficients so that we can kind of express it in the Fourier series. Okay, our Fourier series expansion, that is, we need this kind of expansion for this signal. K is equal to minus infinity to plus infinity, a of k e raised power j k omega naught t. Okay, so we need to compute the coefficients a of k. Okay, so we'll stop this video and we'll continue the analysis in the next video.